It is my great honor today to be able to host distinguished scientist Frank Wilczek to give the colloquium today. Frank did his undergraduate study at MIT, and then he became a PhD student.
Chicago.
Oh, Chicago. Oh. And then he became a graduate student at Princeton. And during his thesis work, he made a major discovery in physics and made the asymptotic freedom of the strong interaction, which eventually earned him the Nobel Prize for physics. And since then, he became a professor in Santa Barbara, where I first met Frank when I was a postdoc, and then at Princeton. You may know there's a book called Who Got Einstein's Office. Frank was working at Institute for Advanced Study. I just asked him, he didn't get Einstein's office, but he got something better. He got Einstein's house. He lived in Einstein's house. Recently, you may have seen there's a TV series called Genius, and they filmed the story of Einstein in Einstein's house. That's the house Frank used to live. And now he is simultaneously professor at 4 different places. For those graduate students who don't understand how a quantum particle can go through that. He is a professor at MIT, professor at Lodita and Stockholm in Sweden, professor at Arizona, and very recently he became the founding director of the TDD Institute in Shanghai. And Frank is really, besides his distinguished Nobel Prize-winning work on strong interaction, he made contribution to almost all branches of physics, in astrophysics, fundamental particle physics, condensed matter physics, one of the co-inventors of the concept of anyon, which was first realized in quantum Hall effect. But very recently, the topic he will talk about today, time crystal, is realized in AMO experiment. Frank, it's a great honor.
Thank you. Well, thank you. It's really inspiring to be here at Stanford, where so many ideas that are extremely significant and provocative and lucrative have originated, and to see so many friends and to have had very interesting conversations in the last couple of days, and I look forward to more over the coming week. So my topic today is symmetries of time. Time is a central element of physics. We can't live without it. And I think it's fair to say that outside of physics, people don't think of time as a material. They think of it as kind of a sequence of psychological events that has some kind of loose structure. But in physics, we can talk about time as a thing, and we can talk about that thing having properties, and it's been very important, certainly in my career, to think about the symmetries of time, and that's what I'd like to talk with you about today. So I'll talk about some older work about the symmetries of time, some present work, ongoing work. It's still exciting, and I think the best is yet to come. And it's appropriate in a discussion of time to talk about past, present, and future. So the first symmetry of time I want to talk about is time reversal symmetry, also called T. This is a classic subject that, in my self-serving point of view, the whole point of it is to lead to axions. So few aspects of experience are as striking as the asymmetry between the past and the future. If you run a movie of everyday life backwards, it does not look like everyday life. The second law of thermodynamics famously captures this idea that entropy increases, doesn't decrease. And here's an experiment showing that if you run a movie backwards, it doesn't look like everyday life. Of course, this one doesn't exactly look like everyday life, even if you run it forwards. But even less doesn't look like everyday life if you run it backwards. Yet, it obeys the laws of physics to a very, very high accuracy. If you look back at the atoms, they're all moving in accordance with the microphysical laws. You find a very peculiar initial state with the ground shaking and dust on the ground for no particular reason. And then it all comes together and makes sense. And the energy that it takes to lift all this stuff, you learn, came from liberation of chemical energy and a building. So macroscopic time reversal is not, in everyday life, time reversal symmetry is just not a feature of experience. Yet, somewhat paradoxically and even problematically, time reversal symmetry was a notable property of the fundamental laws of physics for several centuries, starting with Newtonian mechanics, where you meet second derivatives with respect to time, so you can change the sign, and continuing through general relativity and quantum electrodynamics. They all have time reversal symmetry. Why? Why do you have this gratuitous symmetry that is not necessary to describe experience and yet has featured in the laws of physics? As long as T-symmetry appeared to be an exact fundamental feature of physical laws, it was unclear that asking that question would be fruitful. You can always keep asking why. Any of you who've dealt with a small child know that they'll keep asking why. Why is the sky blue? And you start to talk about scattering of light and atoms, and then they ask why. Oh, Maxwell's equations and quantum mechanics. And then they ask why. And, well, you say string theory. And then they ask why, and they say, and at some point you just have to say, that's just the way it is. That's rock bottom. And if T-symmetry were an exact feature of the fundamental laws, that would have been a sensible answer. That's just the way it is. Okay, it's a very elegant principle, sort of thing you might like to have in the fundamental laws of nature. It just might have been rock bottom. However, that answer became inadequate in 1964 when James Cronin and Val Fitch discovered a subtle effect in the decay of K-mesons that slightly violates T-symmetry. Now, actually, for purists, they found an effect that violates CP symmetry, combining charge conjugation and parity, but there are very profound reasons to believe that CPT symmetry is an exact law of nature, so this could also be interpreted as violation of T-symmetry. And in the intervening years, there have been experiments that directly show violation of T-symmetry. So T-symmetry is not rock bottom, and it's not even quite true, just very nearly so in practical circumstances. Why? Well, this was a profound question, and the satisfying answer is that we've almost nailed it. I should say the almost satisfying answer is that we've almost nailed it. The basic sacred principles of modern physics, relativity plus quantum mechanics, and, sorry, Lenny, local symmetry are very powerful. And when you combine all of them, you find very powerful constraints, very strong constraints on the laws of nature. And what Kobayashi and Masukawa taught us in the context of the Standard Model, which is our instantiation of these principles, is that when you have the particles we actually have with the color and flavor and weak and electromagnetic charges they have, there are exactly two possible sources of T violation. There are exactly two interactions which could give you T-symmetry violation. One of them, which is the one that Kobayashi and Masukawa actually identified, arises when you have three families of quarks, and it beautifully explains what Cronin and Fitch observed, and by now a lot more. starting with the prediction that there are three families, but going on now that the study of heavy mesons and quarks has advanced to describe quantitatively a raft of experimental results. It's been extraordinarily fruitful, and Kobayashi and Masukawa deservedly won a Nobel Prize for their very profound but simple suggestion. But they didn't realize that there was another possible T-violating interaction. This is much more subtle. It's not visible in perturbation theory. And it doesn't happen. To very good approximation. It would represent an interaction between gluons in QCD, which is like an E dot B interaction. It's the analog of E dot B. You don't see E dot B very much in discussions of Maxwell's equations because it doesn't contribute to the classical equations of motion. And so you don't have to worry about it for most purposes. But in QCD, it's very different. When you quantize the theory, you find that this E dot B interaction does play a role, and it is directly violating parity and time reversal symmetry, because E is natural and B is unnatural under time reversal. So why is still open. We have a question. Why is that interaction so small? It's allowed by the sacred principles. We've explained everything else in terms of them. Why not? Why is that still a loophole? Over the past 40 plus years since this became evident, there have been several attempts to explain it, but only one has stood the test of time. Little joke there. And the idea is can be explained non-mathematically, quite simply. It's basically due to Roberto Pecci and Helen Quinn. The idea is to promote the unwanted term, which appears as a number in the standard model as it comes, into a dynamical entity. So you have a coupling constant, G, which is supposed to be outside of time, a universal, eternal feature of the world, and say, no, that's an illusion. It's really G of X and T. It's something that can vary in time. It's a field, like other entities within the standard model, a new kind of field. And if it's a field and the dynamics is right, you could hope that the dynamics drives it to zero. And then you'd have a theory of evolution that tells you why that interaction is not present. Now, what Steven Weinberg and I added to this is to realize that this fix comes with a price, or comes with an experimental bonus, if you like, and a phenomenologically testable consequence. This new field, like all quantum fields, is made out of a new kind of particle. It's a particle I named the axion, in homage to a laundry detergent. There's a little story there. When I was a teenager, I went shopping one time with my mother to get groceries, and there on the shelves was this axion laundry detergent. And already at that time, I was thinking I was going to maybe be a physicist, and if I ever got a chance, and I thought that sounded like a particle. It's really great. It's Greek. It's soft. It's short. It's got the hard sound and everything else. It's perfect for a particle. And I vowed that if I ever got a chance, I would name a particle the axion. And I got the chance because this is a particle that cleans up. It was appropriate because it's a particle that cleans up a problem with an axial current, it turns out. And I told the editors of Physical Review Letters, who were very conservative about naming things, that it was because it has to do with an axial current. I should call it axial. Didn't tell them about the detergent, but here's the it's a true story, and there's the evidence. Okay, so do these axions exist? We still don't know for sure. But what's happened in recent years is that the stakes have risen dramatically. We can calculate that axions, to do their job, have to have very specific properties, and that they would get produced in the Big Bang and survive to this day. They're very, very weakly interacting, very light particles that you can calculate how they get produced, you can calculate how they interact with matter very weakly, and they survive to this day. The relic axion gas has properties that are consistent with the observed properties of the astronomer's dark matter. Astronomy and cosmology, I'm sure you've heard at many colloquia, has this nagging problem that gravity, as reflected in the motion of bodies we can see, is too large to be accounted for by the gravity of bodies that we do see. And so astronomers and cosmologists have been led to postulate that there's a new kind of matter, some kind of dark matter. It's not dark, it's just transparent. And over the years, they've discovered various properties of this matter, but basically its properties are that it doesn't interact significantly with ordinary matter, and it's produced as a cold particle in the early universe, and then just follows gravity. And then you get the right kind of phenomenology. And I should add, that phenomenology that shows that assuming a new kind of particle that's produced cold in the Big Bang has recently been shown to give extraordinarily accurate results for the structure of the universe. There were various advertised problems about cusps and satellite galaxies. There are no problems. So here's the kind of evidence for dark matter that got that story started. The rotation curves of visible objects at the outskirts of galaxies. If the matter just tracked the visible light, would fall off as you receded from where most of the visible matter is, but in fact it doesn't. And you can account for the observations if you have distributed around the galaxy a large halo of this non-interacting but still gravitating stuff. And I said you can find this around the galaxy, but it would be more accurate to say that the galaxy is an impurity in the dark matter, because the dark matter weighs about 6 times as much. And here's a beautiful, there's evidence for this dark matter on many different scales. If you say that you have a theory of this phenomena, there's a lot to account for, and this hypothesis of a new particle accounts for it all. Another kind of evidence is gravitational lensing, where again you find the bending of light that you observe is too large to be accounted for by the gravity of the visible matter you observe. Okay, so the bottom line, after a lengthy analysis of what happens in the early universe and how axions get produced, is that if they exist at all, they must contribute significantly to the dark matter. And plausibly, they dominate it, because it's not so easy to have good guesses for what the dark matter is. This is something we need, and it's a bonus. Several clever strategies for axion detection have emerged. It's not easy. Part of being the dark matter is that it has to interact very, very weakly with ordinary matter, and that's what the theory predicts. And it won't be easy, but many determined people are at work. Here is a photo from the Center for Axion and Precision Physics in South Korea, which is one of several very well-funded, very determined groups doing axion searches. this is the basic strategy for their experiment with an artist's rendition, or my rendition. This is my closest approach to art. So you have axions floating all around in the universe. Once in a while, very rarely, if you have a magnetic field, there's a basic vertex, a basic Feynman graph, if you like, where an axion couples to two photons. If you have a magnetic field, the axion can convert to a photon, and you know how to observe photons. These are actually microwave photons, but okay. Here's another very ingenious proposal. This is called abracadabra, and I used it basically because it's a pretty picture. That's another proposal to set up a magnetic field. This time on a much larger scale. When you have time-dependent axions, they produce effective current interacting with an electric field. They also produce a magnetic field. They also produce effective fields which will generate AC magnetic fields, which you can detect very sensitively with squids. So they're very ingenious proposals. I won't try to do them justice here. Several of them have come out of Stanford, in fact. Another one is that axions can form atmospheres around black holes. You may have read the propaganda that black holes have no hair, but there are certain kinds of things that black holes can have as hair, and axions are one of them. If the axion Compton wavelength is comparable to the size of the black hole, then due to quantum mechanical effects, it doesn't get sucked in. Gets produced if the black hole is spinning, gets produced spontaneously and forms an atmosphere. And this can modify the properties of black holes, modify the gravitational radiation when black holes collide or just when they're moving around. And now that the era of gravitational wave astronomy is well launched, we can look forward to tests of whether these atmospheres in fact exist. So, a specter is haunting physics, the specter of axions. They're out there. The truth is out there. And you shouldn't think of it as scary, though, because they are restoring the balance between the past and the future. And it would be a beautiful end, or beautiful climax to this story of T violation that has had this fascinating, very fruitful history, if it totally unexpectedly led us to an explanation of what the dark matter is. Okay, so now I'd like to turn to the other main symmetry of time, which is time translation symmetry. I'll call it tau. And here the road is not to axions, but to time crystals. Or at least that's where one road leads. So time translation symmetry may be the most fundamental symmetry of all. It says that the basic laws of nature don't change as a function of time. Without that, we wouldn't have science in a recognizable form. We need to be able to do experiments and get the same results the next day, also in the neighboring lab, and so on. But those time translation and translation symmetries are extremely profound and basic to the success of the scientific method. Strangely enough, it doesn't seem to have a less than 7-syllable name, time translation symmetry, so I'm giving it one, tau. I ran out of laundry detergents. Okay. So tau is the principle which instructs us we can discover eternal laws. And it's connected through Noether's theorem, through Emmy Noether's theorem, to the conservation of energy. So pretty basic. Now, modern physicists, when they hear about a symmetry, want to also hear about its breaking and its spontaneous breaking. Spontaneous breaking of spatial symmetry, spatial translation symmetry, is commonplace, and in fact really was the first non-trivial instance of symmetry and its breaking to be studied powerfully in physics and mathematics. Indeed, most common materials like to form crystals at low temperatures and spontaneously will go into the crystalline state at low temperatures, where the symmetry of spatial translations is reduced to a discrete subgroup. Because if you move the crystal a little bit, it doesn't look quite the same until you've displaced each atom to its nearest neighbor. So physicists are accustomed to making analogies and connections between space and time. And so it seems very natural to ask whether there are states of matter that correspond to time crystals. What would that mean? It would mean this is a spatial crystal. You have orderly arrangements of atoms in space. A time crystal would be an orderly arrangement of events in time that some material would spontaneously fall into. A beating heart is a sort of time crystal. The beat is an event that's periodic in time, but it's not very precise. It requires feeding and maintenance, and it's complicated. For physics, if we want something that deserves the name spontaneous symmetry breaking, there are more technical requirements that address these kinds of questions. And a time crystal in the sense of physics should be precise, should not require feeding and maintenance, and ideally should be simple. So we can characterize it completely. So that gives us the question, can tau be broken spontaneously? This turns out to be quite a subtle question. When I first proposed it, I got a lot of flack about it. It's a subtle question, so I'll give them that much. But it's recently borne fruit. The answer is yes. And if you don't believe me, this is the announcement in Science Alert a little over a year ago. The credibility is somewhat undermined because this picture has absolutely nothing to do with the discovery. But a nicer, a more dignified, although still extremely fanciful announcement was made on the cover of Nature less than a year ago, where in this issue, which I have framed right next to the axioms, they were two experiments that announced the existence of time crystals, plus a news feature, plus a news and views, plus a cover. It was quite an issue of Nature. And inside, they have a description of how to create a time crystal, which is at an appropriate level for a colloquium, so I'm shamelessly stealing it. Basically, there are several different variants. Now, this is the simplest with just two states. I should say that these time crystals are not breaking of continuous time translation symmetry. They are systems that are subject to a periodic disturbance, but the physical behavior doesn't reflect that periodicity. It reflects a longer periodicity. And in some of the original experiments, it was a factor of 2. In others, it's 3. By now, many other numbers have been realized. So basically, the phenomenon is as follows. If you have a non-interacting set of spins and flip them with the appropriate pulses, you can get them to go up and down, and if they start up, If you apply the wrong frequency, or if they're not perfectly aligned, then that order will go away after a while. And you'll have normal equilibration. So, however, what's observed in the time crystals is, as a result of interactions, this pattern of up and down, which would be ideal, would happen for the ideal frequency and alignment, actually doesn't go away completely, even when you have the wrong frequency and a random state to begin with. So, and this kind of rigidity against frequency and this long-range order is, for physicists, the hallmark of spontaneous symmetry breaking. To do this, you have to have both interactions between the spins so that they want to behave all together. So ferromagnetic, although antiferromagnetic will also work. And you have to have disorder so that they can synchronize. You have to have a range of possible frequencies they can all agree on. The disorder allows them to do that. And with those two basic ingredients, you can get time crystals. In one of the experiments, this was done by carefully arranged arrays of small numbers of atoms with carefully timed pulses of lasers. In the other, it was much more naturalistic. It was in what's called nitrogen vacancies in diamond, and yet you still get this kind of behavior in a much more natural setting. So the implication of this is that there's a structured equilibrium, that you disturb this system, but the disturbance doesn't result just in heating it up or in a unique equilibrium, that the equilibrium is structured and can oscillate between two different possibilities. And to me, this is the really beautiful thing for a physicist. When you talk about new phases of matter, you want to know what's the phase diagram. And here, as a function of detuning and interaction, you see that there are sharp phase transitions between the time crystal behavior and not time crystal behavior. So, the big picture is that the study of tau breaking is revealing shortcomings in the hitherto conventional view of equilibrium, notably including the emergence of robust, self-organized quantum structures in noisy, randomized systems. And if you haven't had colloquia devoted to the details of these experiments, you really should, because they're very beautiful, and there's much more to it than I've tried to convey here. Usually, technological developments take a long time to come to market, but in the case of time crystals, it's been remarkably fast. In fact, acausal. You can buy time crystals on the internet, and they're used by Doctor Who to travel backwards and forwards in time. Okay, so that's a very interesting branch of many-body physics, and I've just shown you the tip of the iceberg, and it's a growing subject. There have been dozens of papers since those original ones last year, many of them experimental. But I'd like to take things in a slightly different direction here and talk about a different kind of time crystal, if you like, something I find quite fascinating. This is ongoing work. Mechanical time crystals. These are simply dynamical systems that want to move either in their ground state or in any state, depending in different examples. So the kind of systems are very simple. They're ring molecules, or let me not say ring molecules. They're collections of spins, n of them, and we assume that they close up to make a zero. Now this, I don't want to get into technicalities. This can be imposed either as a constraint or as just a selection principle on solutions, and you get different pictures depending on which you do, but let me just fudge those questions. So as a spin system, you can take it as it stands. However, if you interpret these unit vectors as positions in space, this can be an interesting, very unconventional model of ring molecules. Why is it unconventional? It's unconventional because usually when you do the mechanics of ring molecules, you would introduce for every rod not only its position, but also its velocity. But for spins, you don't do that. It's just a spin. Okay. So this is more minimal. You use only the position coordinates to describe the dynamics. And the result of the analysis is that generically, under very general circumstances, if you have the coefficients here, unless they're very, very specially tuned, you'll get motion in the ground state. This is a kind of emergent precession. The different spins make effective fields, and they can make an effective, and they'll all precess around the emergent effective field, as well as wobbling. So here are the equations. These are the only equations I have, I think, in this talk. The crucial thing is that Poisson bracket is not the conventional Poisson bracket. These are not P's and Q's. They're spins, or if you like, one component of spin becomes the canonical conjugate of another. So it's minimal. When people talk about effective theories, they usually don't go this far in pruning degrees of freedom, but it's certainly a logical possibility and leads to very interesting consequences. The equations of motion is therefore simply like this. And then I'll just go to movies. These are different arrays. This is a triangle with the couplings 1, 1, minus 1. Goes around. This is a ring with those. So this is meant to be like benzene with single and double bonds, schematically, that have various strengths. And you see it doesn't rotate, but it's jiggling. You can see if you look very closely. It jiggles. And this is a different thing where we've included a defect, if you like. Then it rotates. Other interesting things when we add volume interactions of this kind, which are also rotationally invariant. A uniform volume interaction gives that. And if you have a volume interaction at the end, you look, well, fancifully something that looks like a flagellum or just a crazy dancing molecule. Okay, so it's, as a model of spin systems, I think it can't be criticized. It's a model of spin systems and those kinds of interactions. As a model of molecules, it's very speculative. It introduces non-commutative geometry. We have different components of the positions not commuting with each other. It's a logical possibility. Whether it's realized in nature is not clear.
These are all classical systems.
This is all classical at this point. Yeah, we'll do the quantum mechanics eventually, but this is all, of course, if it's big enough, the classical system, and if the spin is big enough, it should be a pretty good approximation. Yeah, I'm going to just say one thing in defense of this, is that this kind of motion where the motion in one direction becomes the canonical conjugate of motion in the other direction is the kind of thing you get in a strong magnetic field. It's very sort of thing you get in an emergent form in various forms of the quantum Hall effect. So if you have the right kind of electron wave function and write down the effective theory of nuclei in the presence of that wave function, it's not inconceivable that you would get something like this, although I must say it's probably pretty far-fetched. Okay, so now I'd like to, this is another word I was always hoping to introduce into the English language, TEMI. Its virtue is that if you do cyclic permutations, it's always a word. And as far as I can tell, this is the only four-letter example in the English language. But to make it work, we have to have Temi. So this motivates me to try to think of something that I could call Temi. And just kidding. So I'm going to mix up the past and the future. There are other motivations. So this is trying to take the symmetries of time to another level, if you like, by thinking about symmetries also of time, treatment of time in boundary conditions. Usually in physics we apply past boundary conditions. So if the past state is alpha beta and the future state is gamma delta, we determine gamma and delta in terms of alpha and beta. Now, why I wrote it in this block diagonal form, you'll see in a moment. You could also, if the evolution is unitary or reversible in general, you can also determine the past in terms of the future, in principle. What about treating them on a more equal footing? How about taking some of the past and some of the future and treating them more symmetrically? So, for instance, suppose I give you alpha and delta, can I determine beta and gamma? So, do I get a unique specification of the universe or of my dynamical system by this kind of mixed boundary condition? Well, it's a very simple and pleasant exercise to do this, and this is the answer. So, if D is invertible, then you can indeed take half, not half, it doesn't have to be half, it could be one feature of the future that you build in, but you can invert it and have the future as well as the past boundary conditions influencing the present. As I said, this is unique as long as the determinant of D is not equal to 0. But the determinant of D not equal to 0 is two conditions. It's a complex number, not vanishing. And so generically, it's not 0. Similar to the argument of non-level crossing. That's familiar in quantum mechanics. And in fact, since there are two, even if you have a D as a function of time, the determinant usually will almost never vanish. So this line of thought can lead us through interesting adventures. We can think about a time-symmetric form of Big Bang cosmology, where you have a Big Bang in the past for one kind of matter, a Big Bang in the future for another kind of matter, say that interacts with it very, very weakly. Maybe it's axions. And they won't come into equilibrium, but you can imagine that each, as we know matter in our universe does, organizes into conscious beings who experience the flow of time and have a second law of thermodynamics and so forth, but the arrows would be different.
Won't gravitational interaction between them ruin it?
Well, if they come to equilibrium, yeah. So the gravitational interaction is very, very weak. So I think not generically it won't. You have warring thermodynamic arrows, and this leads to the paradoxes of, okay, I'm moving forwards in time. This other guy is moving backwards in time. We're both sentient beings. I give him a message to kill my grandmother, or something worse. Let's make something kinder. Tell him to ask George Lucas not to make the third installment of Star Wars. Anyway, or give him a better plot. All right, anyway, you can give him So this, at the macroscopic level, there really is such a paradox. But since the framework is consistent, it must have a resolution. Okay. Now, I don't know how to model conscious observers and things that can do this, but I think the only resolution I can see is that when you do this kind of message passing, you wind up on a different branch of the evolution of the universe. So this conceptually leads you into the idea that there are different branches, and if you do this kind of procedure, it just takes you to a different branch of the wave function. Anyway, this is all very speculative at the end. It's the first piece of science I've done whose main application is probably to science fiction. But it's interesting, and you can set up experimental situations where this formulation is relevant. And I'm hoping that in the future, or maybe in the past, some clarity will emerge on these questions, and we'll have yet another brilliant installment in the history of the symmetry of time. Thank you.